Okay, in this video we're going to be looking at how, under certain circumstances, the normal distribution can be used to model discrete data and when it's appropriate to do so. The target audience is really for OCR A single maths or any of the other A-level courses, I would imagine, but certainly for OCR A single maths, this is part of the specification, that you understand the importance of the significance of using the normal distribution if the data is actually discrete. It's a bit ironic that I've been saying for some time the importance of distinguishing between continuous and discrete data and how we deal with it so differently. Discrete tends to be like a bar chart or a stick graph or with a formula perhaps associated with each of the values, and for continuous we're looking at areas underneath a graph to work out a probability within a range. And now we're actually kind of looking at discrete data but using a continuous distribution for it, and it can be done, and it's reasonable to do so in certain circumstances. It's probably best to do through a few examples, but one important thing that we should know is that really the data, the steps between the data values, because if it's discrete there's going to be a step between each value. The step between the data values, often 1, but not always, just because it doesn't, often 1, needs to be small compared to the standard deviation. Otherwise we haven't got enough values. Basically it's all kind of too centered around a few values in the middle. Deviation, if the steps are actually quite big, you might only have very few values, in which case a normal with any significant probability, in which case a normal distribution might not be reasonable. But if you've got lots of values and they're only kind of, and for that you need the standard deviation to be much larger than the steps in between them, then the normal distribution might be able to use. This is not sufficient. I probably ought to write that. Not sufficient. We would need other kind of conditions about symmetry and kind of concentration in the middle to actually justify possibly a normal distribution, but it's not sufficient, but it's definitely necessary. Even if everything else indicates it might be normally distributed, you can't, unless the steps between the data are small compared to the standard deviation, you can't do it. So I'm going to flag that one up, and the rest, and the other conditions, are all to do with the distribution, and you're looking at symmetry, concentration in the middle, and that type of thing. Right, the other thing is, the other important thing, so is to understand that whenever normal distribution is used, what's happening? Am I right in there? It's used for discrete data. A continuity correction needs to be applied. Should be applied. Sometimes it doesn't make much difference, but in practice, in your exam, if you don't, you're going to lose marks, because they want you to understand the importance of the fact that the significance of the fact that it's discrete data being used on a continuous distribution, and that is. And we're going to see this in a few examples anyway. Let me highlight the important things that I think I've just said. First of all, this is a necessary but not sufficient condition for using discrete data, a normal distribution for discrete data. it definitely needs to have small steps. And the other thing is this idea of continuity correction. Okay, and what continuity correction is, and I say we'll see it for a few examples. Suppose, for example, we want to find a probability of it being less than or equal to 54, a particular distribution. Well, discrete means 54, the next one down would be 53, wouldn't it? And then we've got 55, the next one up. What you do when you apply the continuity correction is you extend, to allow for the fact that a continuous distribution is used, you extend the line backwards to allow for the fact that you're actually dealing with a continuous distribution. So you would actually change probability of x greater than or equal to 54, and what I often write is, right, CC, continuity correction, the equivalent of that with the continuous thing is the probability of x is greater than or equal to 53.5. Generally speaking, I tend to like to work with inclusive inequalities when dealing with discrete distributions personally. I tend to like to convert to that and then think about the things after that rather than do it. So I always almost kind of parrot fast and go, even if the question said probability x is greater than 53, I'd probably convert that to an inclusive inequality. That means it's got to be actually greater than or equal to 54. And then when I apply the continuity correction, say that that's got to be greater than or equal to 53.5. But, you know, I've got students who do sometimes successfully kind of know that and skip the middle bit. But I tend to always go to the inclusive, convert to an inclusive inequality and then work from there. Okay, so here we go. One of the most, probably the best examples I can think of here is IQ. IQ scores is actually a discrete distribution in the sense that, you know, the scores range from 100 is the middle score, and they go upwards, but they go up in whole numbers. They go up in discrete amounts, but they are modelled. They're designed in such a way as to be kind of normally distributed. In other words, 68% approximately is within one standard deviation of the mean. So 68% approximately is, you know, between 115 and 85 and so on. So they're actually structured in that way, but it's a discrete distribution. Okay, so this is how we would go about doing this question. Right, so obviously, as we've said before, the probability if it were continuous of getting bang on 100 is equal to 0. But actually, what we actually mean, of course, there for the discrete bit, is it's going between 100 and 100.5 and 99.5. So after applying the continuity correction there, we can say that probability of x lying between 99.5 and 100.5. So that equals 2, and then we can just use the calculator. Again, now I've done the continuity correction, I might put inclusive ones in there to make it consistent or whatever. I keep changing my mind. I'm never consistent myself because I know it doesn't matter. Once you've applied the continuity correction, we're now dealing with the continuous normal distribution, and so it doesn't actually matter whether it's inclusive or not, but I have made it inclusive there. Bringing up the calculator. Okay, bringing up the calculator now, 7, normal CD, and we've got the value of, I've got the wrong menu 7, 2. Right, so the lower value is 99.5, the higher value is 100.5, the standard deviation is 15, and the mean is 100, so that's 0.2659. 2569. Okay, to 4 significant figures. Okay, now, of course, it's a little bit intuitive. If you've got a single value there, you just go 0.5 each side. But I think you do have to be careful with this. So what I tend to do is, when you've got numbers within a range, is draw a number line. And as I said before, I always convert to an inclusive. Always work with inclusive inequalities and convert them to if they're not already. But this one is already anyway. So here we want numbers in the range 90 to 100 and 100. Okay, so it's going both ways, that way and that way. And what I tend to do is actually think of it, so long as we started with an inclusive inequality there, we're actually extending the number line to include that extra 0.5, which is called the continuity correction. So this number here would be 89.5, and this number here would be 100.5. So we're always making it that little bit bigger, going backwards from where the direction of the arrow is. So here, applying a continuity correction, that equals to the probability of it being less than or equal to 89.5 or greater than or equal to 105.5. Oh, sorry, I've got the wrong number there. I said 100, didn't I? I meant it to be 105, so that's 105.5. Okay, so 105.5. Right, so now bringing up the calculator again. Okay, menu, 7, PD. Right, so now the lower is 89.5. The upper is 105.5. Standard deviation 15. Good thing is that with this calculator is it remembers the numbers you put in before. I probably would put the arrow keys down just in case. Yeah, it's 100. So that's 0.4011. Okay, it feels kind of reasonable because, as I say, 68% lies between 85 and 115. Right, now apparently in order to get into Mensa, you need an IQ score of 130, so that's why I put this question in. You need an IQ score of 130. What proportion of that? What probability is that? Well, draw the number line again, 130 upwards. So we're going 130, 131, so on. And so long as you've used the inclusive inequality like that, you're going extending the number line backwards to include the continuous bit 0.5. Okay, so that means it's 0.5, so that's 129.5. Right, so that gives me, so I'm going to apply the continuity correction there. So just write CC, probability that X is greater than or equal to 129.5. So that equals 2, and let's bring up the calculator. I'll do them all. Hopefully you got the idea of how to use a calculator anyway, but let's just do it. Menu 7, 2. 129.5, it's got to be more than that. Okay, so the lower is 129.5. The upper is, right, now the upper, because there's no theoretical end to this arrow, it's going up to, you know, as high as you want, and it's normally distributed, so there's no theoretical top. It can be, but it's got a standard deviation of 15 and 100, so you know, if you put 500 in, it's way above what it needs to be. You don't have to, you know, 400 even, or 300, it doesn't really matter. 200 would be enough. You've got to go sufficiently far away from the center, you know, times by, as long as you're over 5 times the standard deviation away, it's going to be good enough. But you don't have to be exactly 5 times away, so some people just always put the same number in. Okay, so I'm going to put 1,000 in now. I said that 1,000 is definitely big enough. because it's easy to type the zeros in. 15, just checking that the mean is still 100. So, okay, so it's 0.02461. 0.02461. Okay, so the 2.5% apparently qualified to get into Mensa. Right, now finally, this one, the two differences, the inequalities go in a different way. What I tend to do, as I say, some people bypass this, but I'm just very careful with it. It's surprising how confusing this can be, I think. X is less than 95. Bearing in mind the actual distribution that we're dealing with is discrete, so we can say that it's going up in whole numbers. What's the lowest it can be? It can't be 95, it's going to be less than 95. So it's actually going to be less than or equal to 94. Okay, so let's draw that on the number line. Okay, so it's got to be less than or equal to 94. We've got to extend from the actual direction of the arrow backwards. So when we applied the continuity correction, it's 94.5. So applying the continuity correction, that gives us a probability that X is less than or equal to or less than 94.5. Okay, so 94.5, let's put that back into the calculator. Okay, so C, and we put 94.5, and again just scroll down to check that it's remembered the numbers. Yeah, 100, that's fine. 94.5, 0.3569, so 0.3569. Okay, so that's how the continuity correction works. Okay, so just I say my personal preference is to work with inclusive inequalities with the original discrete distribution, and then to extend the number line backwards by 0.5 to allow for the fact that you're using the normal distribution, which is continuous. Hopefully that's clear. Okay, right, one more example, something slightly different. I made this example up. Quite pleased with this one, really. Weight in kilograms of male Great Danes is known to be normally distributed with mean 72 kilograms and the standard deviation 6. That's true, actually. Well, the mean is 72 anyway. I think the standard deviation is around about 6. A database is held in a large chain of veterinary surgeries which records the weight to the nearest kilogram as well as species, breed and gender of its animals. Explain why it's reasonable to use the normal distribution to model the weight of the male Great Danes held on the database. Right, well, I said originally that one of the a necessary condition, so let's write that first of all. A necessary condition is that the steps are small, so the steps are small, are 1, so they're going up in ones, but standard deviation is larger. So let's just standard deviation six large compared to steps between intervals. I think that's fair enough, isn't it? It is large, 6 between intervals. Well, in any case, if whether it's large enough is neither here nor there. The question has said, explain why it's reasonable. So we've got to look for a reason why it's reasonable. And one of the criteria is that the standard deviation is large compared to the steps between the intervals. So that's one of the considerations. Please, please, please do not regard that as the only thing that's important, of course, but it just always is important, and that's why I've mentioned that alone here. But one of the things that people struggle with stats is they want a list of kind of nail it, kind of kind of, I don't know, keyword bingo type thing. And at this level, that's not always possible. We have to think about the actual situation. It might be that you're given some data and it's symmetrical and concentrated around the middle. You could have a question like that where you're given some data and we can see that it's fair, the distribution symmetrical. We can see that there's a high concentration around the middle, and then we can actually look at that, and we can look at that and therefore mention those things. We don't need to do that here, because the other thing is, let's just bullet this as well. The original distribution, because what's that? Remember, the numbers are being rounded, is normal. So there would be two reasons on this particular one. Okay, so it depends. That's why I didn't want to give a list, because if I'd said that the original distribution has to be normal, that might not be the answer in another question, if you get my drift. So that's why I've only given the one criteria that has to definitely apply. It doesn't mean that other things don't need to be mentioned. Okay, explain why a continuity correction is necessary. Well, there we've already said that because the actual distribution is discrete because of the rounding. Distribution is discrete. Okay, because the actual distribution is discrete and the normal distribution is continuous. That might not be the only thing. What you could just say because it's rounded or whatever, but it might get it. But is continuous. Okay, because the actual distribution is discrete and the normal distribution is continuous. Okay, so there's one numeric question I felt compelled to put in this question. The vet is carrying out a program with the aim of identifying and supporting weight loss in its animals. They decide to contact owners of male Great Danes, the weight of which is in the top 10% of those held on its database. Find the least recorded weight that will result in the owners being contacted. Okay, I put this in because, again, you see people putting in, not using the brain, basically. I've seen with this type of thing, people using a continuity correction on the 10%. That would be nonsense, of course, because the continuity correction applies to the x value, the actual value, not the proportions. So we're using the inverse normal, and just let's see what we get from using the inverse normal. So let's just bring that up. So menu and 7, inverse normal. Right, so we want the top 90%. Okay, top 90%. I've still got the data in from the standard deviation example there, from the IQ example. The standard deviation is 6 for this distribution. The mean is 72. So we get the number 79.68 or 69. So putting that on the distribution, what we've got for the actual normal distribution, 79.68 is the actual value of the norm on the normal distribution that has 10%. But of course this is discrete, so we're going for the largest one above that. So because basically the actual data is the graph of it's going to look more like with 72 in the middle, 72 in the middle, and they're going to go down like that, 73, and then finally we've got 10% of them going over here, and the smallest one will be 80. So the answer is 80 kilograms, smallest. That smallest recorded weight in top 10%. So there was no, this wasn't really about continuity correction. It was just about basically interpreting data and working properly with the kind of questions we're given, with the kind of information we're given. Okay, so that's it. Very important, that often gets missed out. We're going to, another thing we're going to go on to in the next video, and you may have noticed that the binomial, particularly if the p is equal close to 0.5 or close to 0.5, is almost like a discrete equivalent to the normal distribution. So we're going to be covering the kind of connection between binomial and normal distribution in the next video. Okay, so but that's it for now. Bye.